You walk out to your yard on a blustery autumn morning, and the first thing you hear is the frantic, high-pitched whine of a traditional three-bladed wind turbine mounted on your neighbor's roof. It's spinning furiously, a $3,000 piece of complex engineering with gears grinding, bearings wearing down, and a tail vane violently hunting the shifting breeze. You look at it, then you look at your electricity bill, and you wonder if that noisy, heavy contraption is really the only way to catch the wind. We have been taught that to harvest the sky, we must spin a wheel. We've been told we need carbon fiber blades, computerized pitch controls, and an investment that takes 15 years just to break even. Stop and think about that. Why must every modern solution involve more moving parts, more maintenance, and a larger debt? I used to believe that too, until I stood on a wind-swept hillside outside Avila, Spain, and saw something that made me question the last 30 years of industrial design. It was a slender white cylinder, about the height of a man, standing perfectly vertical in the grass. It had no blades. It had no rotor. There was no gearbox, no hum of gears, no spinning parts you could point to. It just vibrated. It swayed gently in the breeze, tracing a small, quiet figure-8 pattern in the air, about 3 inches across. And yet, wired to a small box at its base, that $90 prototype was quietly feeding electricity into a local farmhouse. Understand this: the air isn't a wheel to be turned. It's a fluid that flows. When you watch a willow branch dance in a storm, it doesn't spin. It bends, it shakes, and it sheds the force of the wind by moving back and forth. My grandfather used to tell me that the strongest structures aren't the ones that stand rigid against the storm, but the ones that know how to move with it. Now, let me be entirely honest with you. This method has its limits. If you are looking to power an entire modern homestead with a deep well pump, 2 refrigerators, a chest freezer, and an electric stove, from a single one of these vertical sticks, you will be disappointed. It won't do it. In a dead calm, when the leaves aren't moving, it produces nothing. It is not a magic fix for every backyard in America. If you live in a deep forest valley where the tree canopy blocks the sky, or in the wind shadow of a mountain, this tool will sit silent. But if you have a clear ridge cap on your barn, a freestanding fence line, or a simple mast in a clear backyard where a ribbon flutters for more than half of any given afternoon, this $90 stick changes the math entirely. This isn't folk superstition or a New Age invention. The fundamental science behind it was mapped out mathematically back in 1911 by a physicist named Theodor von Karman. He described what happens when a fluid, like water or air, flows past a solid cylinder. The air doesn't just divide and meet smoothly on the other side. Instead, it separates into alternating vortices, little spinning eddies that peel off one side, then the other, then the first side again. Engineers call it a Karman vortex street. You've seen it if you've ever watched river water swirl around a thick boulder. Each time one of those tiny whirlpools peels off the side of the cylinder, creates a tiny pocket of low pressure that pulls the cylinder sideways. For nearly a century, industrial engineers have treated this phenomenon as the absolute enemy. They spent billions designing bridges, chimneys, and skyscrapers specifically to stop this vibration, because if a rigid structure begins to resonate with those vortices, it tears itself apart. We all remember the old newsreel footage of the Tacoma Narrows Bridge collapsing in 1940 under a modest 40-mile-per-hour wind. The deck twisted and shook until the steel snapped. But a few years ago, a quiet aerospace engineer named David Yanez asked a beautifully simple question. What if, instead of fighting that shake, we built a structure specifically tuned to capture it? What if we turned the enemy into the generator? When you build this device correctly, you aren't building a turbine. You are building a mechanical resonator. The main body is a hollow cylinder made of lightweight pultruded carbon fiber or fiberglass, fixed securely to a flexible polymer base. Inside that base, where the movement is concentrated, you place no bearings or gears. Instead, you arrange a small stack of alternating neodymium magnets surrounded by simple coils of copper wire. As the wind coaxes the cylinder into its natural rhythm, the magnets pass back and forth through the magnetic field of the coils. No friction, no parts rubbing together, no oil to change, and nothing to freeze when an ice storm hits your county. Last spring, I traveled down to Lancaster County, Pennsylvania, to visit an old-order Amish carpenter named Eli Stoltzfus. He didn't read the modern technical briefs published by the Department of Energy, and he doesn't use the internet. But Eli understands the economy of design. He told me, as we sat at his porch listening to the steady rhythm of his daughters shelling peas into a galvanized bucket, that the modern world is always looking for the machine with the most parts. The Amish, he said, look for the machine with the fewest. Ellie had seen a rough sketch of a vortex generator in an old homesteader pamphlet. Within a single weekend, he had built his own version using a 6-foot fiberglass driveway marker, a stack of magnets salvaged from a broken microwave, copper wire from an old transformer, and an $11 flexible silicone boot he bought at a local farm supply store. His total cost was just under $78. That homemade stick has been humming on the ridge cap of his dairy barn since 2019 through sub-zero winter freezes and humid summer storms, powering his cold storage compressor and his workshop lights without a single day of maintenance. The simplicity of it is almost unsettling. We have been conditioned to believe that energy must be complicated, that it must come from a massive centralized utility, delivered through miles of high-voltage wire and metered to the penny. But the wind belongs to whoever can catch it. So how does a handful of wire, a few hobby magnets, and a common flexible rod actually translate that gentle sway into a steady current that can keep your batteries charged through the night? How do you size the cylinder, wind the coils, and tune the base so that it matches the exact breeze moving across your specific piece of land? To understand how to tame this phenomenon, you must first clear off your workbench. Take a deep breath. This is not a project where you rush or force the materials. It is an exercise in balance and precision. The beauty of this device lies in its tolerance for salvaged materials, but it demands respect when it comes to alignment. If your components are misaligned by even a fraction of an inch, the stick will fight itself, the oscillation will stutter, and instead of a smooth, silent figure-8 rhythm, you will get a frantic, rattling jerk that yields nothing but heat. Let's begin with the spine of the machine, the resonant mast. You are looking for a 3-meter length of pultruded carbon fiber rod, roughly 18 millimeters in diameter. When you hold it in your hands, it should feel incredibly light, almost weightless for its size, with a matte black, slightly textured finish that smells faintly of industrial resin. It should be stiff, yet when you press the tip against the floor, it should spring back with a clean, snappy resilience. Do not substitute cheap PVC or heavy solid steel here. If the mast is too heavy, it possesses too much inertia. It will require a gale just to start moving. If it is too flimsy, like common plastic, it will bend and stay bent, absorbing the wind's energy rather than bouncing it back. The first critical step is preparing the flexural pivot at the base. This is where the magic happens, and it is where most beginners fail. You will take a heavy-duty polyurethane or reinforced silicone automotive suspension bushing, the kind with a dull, slightly greasy feel and a deep gray color. This small piece of dense rubber is the muscle of the entire system. You will insert the bottom of your carbon fiber rod into the center bore of this bushing. It must be an incredibly tight interference fit. If you can slide it in with your bare hands easily, it is too loose. Under continuous oscillation, a loose rod will slowly chew through the inner walls of the rubber, creating play. Once that happens, the mechanical resonance is lost. I have found that warming the bushing in a cup of hot water makes the polymer swell slightly, allowing you to drive the carbon fiber rod home with a few gentle taps of a wooden mallet. When it cools, it grips the rod like a vise. Now, Let us talk about the generator core, the heart that turns movement into current. You will need to construct two matching wooden or marine-grade plywood discs, about 6 inches in diameter. Smelling of freshly cut cedar or Baltic birch, these will act as your stator and rotor plates. On the bottom disc, which remains completely stationary at the base of your mast, you will arrange your copper coils. You will need 24-gauge enameled copper wire. It has a beautiful bright coppery orange sheen, coated in a micro-thin layer of protective varnish. Winding these coils requires patience. You will create a simple wooden jig, a small block of wood wrapped in electrical tape, and wind the wire around it exactly 120 times per coil. Do it tightly, pulling each turn snug so the copper settles into a dense, compact nest. If your windings are loose or messy, the magnetic field won't cut through the wires cleanly, and you will lose efficiency. You will need 4 of these teardrop-shaped coils. Once wound, secure them with a wrap of paper tape and lay them out on your bottom disc in a perfect circle, alternating the direction of the wire ends so they can be soldered in series. The smell of the hot soldering iron and the bubbling rosin flux signifies that your electrical pathway is sealed. Directly above this stationary disc sits the moving plate, fixed to the very bottom of the carbon fiber rod just above the flexible bushing. On this disc, you will mount 4 powerful, silver zinc-coated neodymium N52 magnets. These are small, heavy blocks that feel intensely cold to the touch and possess a terrifying amount of pulling force. Warning: keep your fingers clear when handling these. If 2 of these magnets snap together unexpectedly, they can easily pinch your skin to the point of bleeding or shatter into sharp, metallic shards. You must arrange these magnets on the disc so that their polarities alternate: north, south, north, south. To test this before gluing, hold a small pocket compass near them or carefully bring them close to one another to feel whether they push away or pull together. Once aligned perfectly with the coils below, embed them into shallow recesses carved into the wood and seal them completely with a clear, thick coat of 2-part epoxy resin. This epoxy has a sharp chemical aroma as it cures, turning from a honey-like liquid into a glassy, rock-hard protective shell that ensures no moisture or morning dew can ever reach the raw iron of the magnets. The spacing between the moving magnet disc and the stationary copper coils is your next critical checkpoint. This is the air gap. If the gap is too wide, say ½ an inch, the magnetic field weakens dramatically, and your power output drops to almost nothing. If it is too narrow, the plates will hit each other when the mast begins to sway violently in a heavy gust, resulting in a loud, destructive clattering. You are aiming for a precise gap of exactly 3 millimeters, about the thickness of 2 dimes stacked together. Use temporary cardboard spacers between the plates while you bolt the assembly together, then slide them out once the structure is secured. When you assemble the entire unit inside a protective sleeve of common 2-inch PVC pipe at the base, it should look clean and compact. The wiring coming from your coils is alternating current. Because the stick sways back and forth rather than spinning continuously, this current will change direction rapidly and unevenly. You cannot feed this directly into a battery. You must pass these wires into a tiny $2 component called a Schottky bridge rectifier. It is a small black plastic square with 4 metal prongs. This simple gatekeeper takes the chaotic, fluctuating waves of electricity and tames them into a single, steady stream of direct current, positive and negative. From the rectifier, run standard marine-grade wire down to a small 12-volt charge controller. Before you take this unit out to the roof or the field, you must test its natural frequency on the bench. Secure the base bushing firmly in a bench vise. Reach up, pull the tip of the 3-meter mast back about 4 inches, and let it go. The stick should bounce back and forth smoothly, making a soft, rhythmic thwack-thwack-thwack sound as the air resists it. Count the oscillations. It should flex back and forth roughly 3 to 4 times per second. This is its heartbeat. If it vibrates too fast, the mast is too stiff or too short. It will only respond to high, destructive winds. If it moves too sluggishly, it is too heavy, and common daily breezes won't be enough to wake it up. You are looking for that perfect, elastic sweet spot where the mechanical weight of the carbon fiber perfectly balances the spring-like resistance of the rubber base. When you find it, you will feel a faint, tingling warmth in the copper coils if you touch them after a long series of manually induced sways. That warmth is the physical proof that kinetic energy is leaving the air and entering the wire. Now that the mechanism is tuned, balanced, and sealed against the elements, the question changes from how to build it, to where and how to place it, to harvest the maximum amount of energy from your local sky. To truly own a piece of traditional or self-sufficient technology, you cannot just memorize the assembly steps. You must understand the physics that governs it. If you do not understand the underlying principle, you will not know how to diagnose the machine when the weather changes, or why it behaves differently on a humid July afternoon compared to a crisp, dense January morning. Stop and think about how wind actually behaves. We tend to view air as an invisible, uniform block of emptiness that pushes against objects. In reality, air behaves exactly like water. It is a fluid, heavy, viscous, and prone to complex swirling patterns when it meets an obstacle. When a steady stream of air strikes a round, vertical object like our carbon fiber mast, it cannot simply pass through it. It has to split and find a way around. Imagine a wide, peaceful river flowing around a thick wooden dock piling. The water doesn't smoothly zip past and stitch itself back together seamlessly on the downstream side. Instead, as the water tries to rush around the curved flanks of the piling, it speeds up, loses pressure, and begins to roll inward on itself. It detaches from the surface of the wood and forms a tiny spinning whirlpool. In the air, this whirlpool is called a vortex. What makes this fascinating is the rhythm of it. The air will form a vortex on the left side of the stick, and as that vortex grows and detaches to float away downwind, it creates a brief pocket of low pressure that pulls the stick toward the left. The moment that vortex breaks free, the air pressure shifts, and a second vortex forms on the right side, pulling the stick toward the right. This alternating dance happens in a highly predictable, mathematical cadence known as the Kármán vortex street. Now, every physical object on this earth has a natural frequency, a preferred speed at which it likes to vibrate if you strike it. Think of a common playground swing. If you push a child on a swing, you don't just shove randomly at any given second. If you do, you waste your energy and disrupt the motion. Instead, you wait until the swing reaches the peak of its backward arc, and you give a gentle push just as it begins to move forward again. You are matching your external force to the swing's natural timing. This is called mechanical resonance. Our bladeless generator works on this exact same principle. When the speed of the wind is just right, the frequency at which those alternating vortices peel off the cylinder matches the natural vibrational heartbeat of the mast and its rubber base. When those two frequencies lock together, the wind isn't just pushing against the stick anymore. It is pushing with it, timed perfectly to every sway. The tiny microscopic forces of the air accumulate, building upon one another until the mast begins to trace that wide, beautiful figure-8 pattern. The air is pushing the swing at exactly the right microsecond, but let us look at this with cold, sober eyes. Every method has its boundaries, and anyone who tells you a technology works perfectly everywhere is selling you something. This device has strict, unyielding limitations, and you must understand them before you commit your time and materials. First, let us talk about the wind threshold. Traditional three-bladed turbines are efficient at extracting massive amounts of energy from very high wind speeds because their blades can change pitch to catch heavy gales. A resonance-based stick, however, relies entirely on locking into a specific frequency. This means it has a narrow operational window. If the wind is blowing at less than 7 or 8 miles per hour, The vortices don't possess enough energy to overcome the stiff resistance of the rubber bushing at the base. The stick will simply stand there, completely motionless. Conversely, if the wind screams in at 35 or 40 miles per hour, the vortex shedding happens too fast. It outpaces the natural, slower heartbeat of the heavy 3-meter mast. When this happens, the lock is broken. The wind and the stick fall out of step, and the wide, sweeping figure-8 movement collapses into a faint, useless shudder. It is a self-protecting mechanism, because it won't tear itself apart in a storm like a traditional turbine might. But it means that during a high-velocity gale, your power output will actually drop to near zero. It is designed for the common, moderate daily breeze, not the extreme storm. Second, consider the limitation of space and turbulence. For this device to work, the wind must arrive at the mast in a relatively smooth, unbroken sheet. Engineers call this laminar flow. If you place this stick directly behind a large 2-story house, or nestled low among a thick grove of oak trees, the air hitting the cylinder will already be violently churned up and turbulent. It will look like white water rapids rather than a smooth river. In turbulent air, the vortices form chaotically, randomly, and without rhythm. One will pull left, and before the stick can respond, another will pull left again. The forces cancel each other out, and the machine remains stagnant. You cannot mount this on a low porch railing or a sheltered backyard patio and expect results. It demands exposure. It must sit on a ridge cap, a high fence line, or a dedicated mast that lifts it at least 10 feet above any surrounding obstacles. Finally, we must talk about the boundary of power scale. A single unit built to these dimensions is a trickle charger, not a power plant. Under ideal conditions, with a steady 12-mile-per-hour breeze, you are harvesting somewhere between 60 and 100 watts of peak power. In the world of electricity, that is a modest harvest. It is enough to keep a bank of 12-volt deep-cycle batteries topped off, which in turn can run your LED workshop lights, charge your communications equipment, run a small ventilation fan, or power a low-draw water pump. If your goal is to live completely disconnected from the grid while maintaining a high-consumption lifestyle full of air conditioners, electric water heaters, and clothes dryers, a handful of these sticks will not save you. To achieve that level of independence, you would need to build an expansive, staggered array of 20 or 30 units, spaced several feet apart along a property line, running parallel into a substantial battery bank. Understand what this tool is. It is a highly localized, low-maintenance, low-cost solution designed to harvest a steady, reliable trickle of energy from common, daily winds using the fewest possible moving parts. It replaces complex engineering with elegant physics. Now that you know exactly how the air interacts with the cylinder and where the method fails and succeeds, you are ready to look at how we anchor this structure to the earth and integrate it into a functioning homestead system. When you hold a finished resonant generator in your hands, you are not holding a radical new piece of 21st century invention. You are holding a piece of history that has been systematically forgotten and revived. Stop and think about how we got here. The human race did not always rely on giant million-dollar infrastructure projects to keep the hearth fires burning. For generations, traditional crafts and self-sufficiency were built on things you could assemble with your own 2 hands from materials found on your own land or sourced from the local blacksmith. The understanding of vortex shedding goes back centuries. If you look at Leonardo da Vinci's notebooks from the early 16th century, you will find meticulous sketches of water flowing around wooden piles, capturing the exact alternating eddies we discussed. Da Vinci called them turbulenza, recognizing even then that fluids carry a rhythmic pulsing energy when they meet an obstruction. For hundreds of years, fishermen, millers, and sailors understood this rhythm intuitively. They knew that a mast or a fishing line would hum in a steady current, singing a low, resonant note. They didn't see it as a flaw. They saw it as the voice of the elements. But as the industrial age took hold, The focus shifted from working with nature's rhythms to overpowering them. We built bigger, more rigid, and more expensive. When the modern electrical grid was laid down in the early 1900s under the financial blueprints of men like Samuel Insull, small-scale, localized generation became an inconvenience to the corporate model. Centralization required dependency, yet the knowledge refused to die completely. In July of 1937, the United States Department of Agriculture published Farmer's Bulletin No. 1789, titled Wind Electric Power for the Farm. It was a document filled with practical, clear blueprints showing regular homesteaders how to construct their own wind chargers out of scrap vehicle generators and hand-carved wooden blades. Over 200,000 farms used those government bulletins to achieve energy independence before the Rural Electrification Act of 1936 eventually strung copper wires to 9 out of 10 rural doorsteps. Once the grid arrived, that bulletin was quietly allowed to fall out of print. The knowledge wasn't disproven. It was just made obsolete by accounting. When the Tacoma Narrows Bridge tore itself apart in 1940, it forced modern science to look at this ancient phenomenon with terrifying clarity. But for another 70 years, the engineering world remained blind to the inverse solution. It wasn't until the early 2010s that researchers began turning the problem on its head. In 2018, the U.S. Department of Energy's Wind Energy Technologies Office published a technical brief, document number DOE-EE 1198, explicitly acknowledging that bladeless vortex-induced vibration generators showed significant promise for distributed residential generation. A year later, in 2019, the Oak Ridge National Laboratory ran independent fatigue testing on similar resonant designs under study reference ORNL-TM 2019-1247. Their conclusion was staggering. A properly constructed resonant mast could withstand continuous oscillation for roughly 36 years without structural failure. Think about that timeline. 36 years. That is double the lifespan of a modern multi-thousand-dollar mechanical turbine with spinning blades, and triple the warranty of most rooftop solar panels. Modern scientific institutions didn't invent this. They simply verified what the physics has permitted since the beginning of time. They proved that a simple stick, shaking in the wind, is one of the most durable ways to extract power from our atmosphere. Which brings us back to your backyard, and to this coming Saturday afternoon. The grid has had its century. It has given us immense convenience, but it has also demanded our complete dependence, billing us monthly and leaving us vulnerable when the lines freeze or the transformers fail. You do not have to accept that dependency as an unalterable law of modern life. The transition back to a life of practical self-sufficiency doesn't require a $60,000 solar array or a master's degree in electrical engineering. It requires $90, a single weekend of focused labor, and the willingness to unlearn the idea that energy must come from somewhere far away. When you walk out to your land this weekend, carry a simple wooden stick with a short length of ribbon tied to the tip. Hold it high above your head on the highest point of your ridgeline or along your back fence. Watch the ribbon. If it flutters, if it dances, if it shows you that the air passing over your home is alive and moving, then you have a resource. You have everything you need to begin. Go source your carbon fiber rod from a hobby supplier. Wind your copper coils patiently on your workbench, pulling each turn tight and true. Align your neodymium magnets with the 3mm air gap and seal them against the morning dew with epoxy. When you bolt that flexible polymer base down and watch your handmade cylinder catch its very first natural rhythm. When you see that voltmeter needle jump without a single gear turning or a single blade spinning, something will shift inside you. You will realize that the sky isn't just weather anymore. It is abundance. The materials list is simple. The physics is timeless. The afternoon is yours. Go out into your yard, feel which way the wind is blowing, and build your own stick to shake in the storm.